System Validation with IDS-Fpga. I'm your host, Neena Sandavle. Agnesiss is a leader in electronic design automation, delivering solutions for complex design and verification problems in system development. In this webinar, we will deep dive into a complete design flow demonstration using an Ethernet generator and monitor example. As a reminder, everyone will receive an email with instructions on how to review the PDF and recording for today's webinar. We will also be taking some time at the end of the webinar to answer your questions. So please do use the questions panel. Please welcome our presenter for today's webinar, Freddie. Freddie is an established applications engineer here at Agnesiss. He has specialized in the FPGA development. Over to you, Freddie.
Nunez, and today we're going to look at accelerating FPGA development from specification to system validation with IDS-Fpga. So this is kind of the agenda of what we're going to go over today. We're going to look at a typical SoC assembly, which kind of looks like that for an FPGA. The challenges of an FPGA flow. We're going to see if there's any other better way to kind of go over these flows. And then we're actually going to look at the IDS-Fpga flow. So kind of our solution to the FPGA flow. In doing so, we're going to look over kind of an example of an Ethernet generator monitor and go through the IDS-Fpga flow with this example. And we're going to show the integration of IDS-Fpga genetic collaterals in our FPGA project. So here we have a typical SoC assembly. So you can see it's very similar to how you have an FPGA. I guess you have your CPU and your different subsystem, and then there's a different programmable IPs or IPs with memories that could be connected to that. And we see that that can be connected to the AXI HB interconnection. And then down the line, those are going to hit your targets, in this case, these APP targets, and they could be connected to, say, some type of sensors to the external world. So right now, primarily, we're going to be looking at these programmable registers in these IPs. So now kind of looking at the challenges of FPGA flow, one thing that can be a challenge to some users is a new user required to learn new flows for integration of these IPs. So if you have IPs that you need to integrate in tools, sometimes there's different mechanisms to do that. It could be different for different companies, but you kind of want a flow that's easy to use, good for ramp up, and kind of has some reusability. And then the next thing is that when it comes to the process, there's going to be different teams. So there could be miscommunication for different teams. So, you have your DVs, you have your software firmware team, some people that are just allocated looking at the documentations. And if there's miscommunication between these different silos, that can increase the time to market. So it'd be best if, say, there was one central document or say one specification where you can get all these different kind of collaterals and the team can collaborate based on this one spec. So is there a better way kind of to get rid of this headache? So one thing that IDS-Fpga can do is accelerate the learning curve for FPGA software. So that adding to our integration of our generated collaterals into, say, Vivado or Altera. This can be done using automation and automation from a single spec. So that helps prevent error and increase productivity, because if you have one central spec, then all the generated collaterals are going to be the same for, say, your DB team, your firmware team, because it's all being generated from a central spec. So IDS-Fpga is going to generate the design code for the registers with a variety of different bus interfaces, along with interconnectivity. And besides just these generated collaterals, we also can provide verification and simulation environments with these collaterals. So now let's look more into this specification-based flow. So in this flow, you can see what we're doing is we're taking one flow. In this case, we're going to have an IDE, and we're going to generate different collaterals. So we're going to generate RTL, different buses, UVM RAW, UVM sequences, verification environments, C headers as well, along with documentation and some environments to test these on. And we can see that it should be cross-platform. So different teams might be using different OSs. So this will work across all your platforms, Linux, Windows, and Mac. So this is more looking to the IDS-FPGA flow using Vivado in this case. So here in the center, you can see we have GUI-based register and test sequences. So what this is coming from is we're gonna create a central specification, and we'll see a little later how that's done. And you can see from this, we can generate a lot of different collaterals. So we could generate IP blocks that can be done in different RTL formats, so Verilog, VHDL, System Verilog. And along with that, we could do some interconnects. So along with just generating these blocks, we can do create interconnection between different blocks, and we could do something called a mirror block, which we'll show a little later. And again, all those collaterals are going to be imported to Vivado, and then we can create different packages with those, so that lends the reusability. And again, for a later validation, after everything's in part of Vivado, we can export that and we can create our XSA file, and then we can move that into Vitis. Another cool thing we do from the central spec is we can create C-tests. So these can either be automatic, created by IDS-Fpga, or you can use a sequence template to create your own custom-based sequences that you can let it test down on the Vitis platform. Along with this, we also have a verification environment. So there's a complete UVM environment and a validation environment, and that's a RISC-V based C environment. Later, this is we're working on getting this on ARM as well. But you can see how powerful this single spec is, because we can generate multiple different collaterals and test different things from verification and validation, all from our one central spec. So now we're looking at this block diagram for the Ethernet example. So here we have this EthGen1 IDS block. So this is what's created from IDS itself. So we're going to see a little later from the specification. And then we have, so that's just denoted by this orange block. And then we have, for further testing, some custom made blocks. So Ethernet generator block and Ethernet monitor block. And then we can see that another signal is coming out from this EthGen module, and it's called a terminal loopback. So again, that's just further testing that we're going to do for this example. And here you can see that to communicate on the CPU side, we have a AXI4 Lite interface. So now kind of going to how that flow in IDS-Fpga works, especially with Vivado. We can see that Vivado has the capability to create custom buttons. So these buttons allow for quick and easy use commands or execution or to run scripts. So we can create these buttons, and then IDS-Fpga will attach certain commands to them. So we can utilize these commands to do something like launching our register IDE that we'll see, all of the other commands associated with IDS-Fpga, or we can run some scripts that are later generated for the import of IP blocks or to create connections. So with these custom buttons, we can open our IDS-Fpga register template directly from Vivado, and we can create our specification and generate multiple different collaterals in the ID. So RTL, C header, test sequences, a verification environment, and a validation environment. So here we're looking at IDS-Fpga, the IDE itself. So this is a template-based way of defining these registers. So you have this IDE. It's gonna here it just populate with some registers. These registers displaying different functions. We can define multiple different registers with different field widths. We could do different names, software and hardware access types, default types. So these are all just a method of creating a register specification. But now going to the configuration itself, there's a lot of different ways to configure it. So we can see that there's different collaterals that can be generated using this IDE. So we can generate against our RTL, our verification collaterals in the form of UVM, and some verification environments. We can generate C headers and a documentation. And then going to just the configuration itself, there's different bus types that can be created. So these are those bus interfaces, along with some other kind of stuff that we have for limiting the size of some blocks, default C type, defining your endian. And then next coming up, so besides the register specification, we also have this sequence template. So we could think of this as a sequence specification. So what we're doing in this case is we're doing a bunch of register writes with certain values. So this is doing the initializing of our Ethernet monitor example. So here it's again part of the IDE. It's dynamically taking all the information from that register specification as well. So we can see that how it's being done here. And what's happening here is we kind of have a kind of pseudocode format where you can see we're just doing a write operation to a certain register and adding a value. Again, this could be more complex. There's mechanisms here for loops, while loops, for loops, wait statements. So again, this can get really complicated, and it just a powerful tool to kind of create your own custom sequences. You can also do configuration for the sequences themselves. So again, this example is kind of looking into Vivado. So you can customize the seek signatures here. So this will be going into later down when we go into the \Vitis platform. But you can see for our register writes and reads, what we're doing is we're using the AXI out 32 and the XIL in 32. So these are APIs for the \Vitis platform. And now these are going to be the default signature for our read and write operations. And then now going to a verification environment. So along with just generating all the other collaterals, we can generate the design components and the RAL. We could generate standard sequence for registers. So these are just some that we created based on your register specification. And if any special properties are applied to it, if you have any case for special registers, say alias shadow, those sequences are going to be applied there. Before we showed those custom test sequences. So that's exactly what was showed before in the IDE. So again, those sequences can also be run in our verification environment. So when they're generated, they're also included in the verification environment. And there's other things that can be added in that UVM test environment, including like backdoor access through H2 path, different cover groups, constraints, and legal bins. And this is kind of a push button mechanism of doing this because we have make files for different simulators. So it's kind of a easy to use, easy to ramp up verification environment for your engineers. So now we can see what the tool can generate. So now let's see the application of that in your FPGA flow. So now we're going to look into the integration of IDS-Fpga generated collaterals. So again, what we just did is we went into that IDS-Fpga IDE, and we've already specified design, and now we generate collateral. So what's next? So what we have next is through some scripting that we have available is we're going to create a top level wrapper and mirror blocks for our designs. After that, we're going to do the packaging and importing of our generated files. And then we're going to go into the block designer and automatically create the block design and all the connections associated with that design. So again, going back to those custom buttons, we have them here. We'll click the button in this case, and we can see all these scripts are being initialized. So we can see what's happening in the background. We see all the, in this case, the mirror block being created and all the connections being created. So what this is doing is it's reading all those files that we generated and then creating an associated script that's later going to be used to instantiate these blocks in our block designer. Next here, we can see that we're creating the connection script. So again, it's from that mirror block and that top level wrapper that was just being generated. This is just creating all the interconnections between them. That's later going to be used for this design. So now, so those two blocks, what they did is they took all the generated collaterals, got all the paths associated with them, and I created a script in order to kind of initialize this. So after running one of them, we see that we took those all those generated collaterals and we packaged them as IP. So the nice thing about it being packaged as IP is that you can see it's all here clear and done, and that IP is just now ready to be used in your design itself. Additionally, this IP can be reusable as well when because it's IP that's been packaged, you can again just use this down the line for any other project that you have that might have a similar use case for this IP. So now that we have that IP package, we're going to run our next connectivity script. So in this case, you can see this is one block created by IDS. and then the other mirror block that'll also be created by IDS. So what it's doing is just creating a mirror of that block that we specified in the ID itself and create a one-to-one mirror. So in this case, for the mirror, the inputs are connected to the outputs and outputs connect to the input. And again, in this use case, we imported some additional things we need for our design. So that includes our Zinc processor unit and then a processor system reset. So addition to after this, I guess the hard part's done. Hard part done by IDS-Fpga. And now we're gonna just run the Vivado block connection and automation. So simple like that. After all the specifications created, we're just gonna run a couple scripts. Again, also generated by a tool when we see that we have this design already created. So it's just as simple as pushing a couple buttons, and we can see that we create this complete design for this Ethernet model that we were looking for. So now that we have the design created, the next step again is to run the synthesis, implementation, and generate the beat stream so that we can actually target our board. But along with that, we can take it maybe one step forward and we can export our design as XSA, and we can do further validation using वेविनाIds. So वेविनाIds is more on the software side, the software platform. So that's kind of now going to those C headers that we were talking about earlier. Along with the C headers, again, we showed that custom sequence template, and this is, again, the code generated for that. So you can see here, we have all our includes. And what we're doing here is, again, we're just doing some simple read operation to initialize our Ethernet generator monitor design. And we can see after this was run, we run this, we target our platform, and we see that just straight out the box after that specification for the sequences is created, you see that this is now working on the VIDIS platform itself using the C headers and the sequences that were generated prior. So to wrap it all up, what's the use of IDS-Fpga? So using the specification-based flow for IDS-Fpga, teams can shorten the development time, we're thinking by at least 30%. And this is again done because we're using correct by construction code from a specification. So we have guaranteed that this code is working because it's created by IDS-Fpga. It itself has checks that's going in, doing stuff for semantics and making sure each names are unique. There's no overlay. And again, with the specification, we're not just generating one output, we're generating multiple for multiple teams. FPGA can improve the FPGA development flow and how it can help you save time and resources and kind of headaches between the teams. So our recommendation is adopting a specification-based approach for these FPGA designs, and hopefully that's going to help you reach market faster with better quality. So again, at least FPGA, it's helping out the flow, and we just want to help your team automate the registration design process for your FPGAs. So if you do have any questions, please check out our product page for IDS-Fpga. If you have any more details, if you want to see demo, or if you want to have an evaluation of the tool. So now we'll go to the Q&A section.
Thank you, Freddie. So we do have some questions. Just a reminder to our attendees, if you have any questions about today's webinar, please enter them in the questions panel. And now to the questions. The first question is, what all outputs are included with IDS-Fpga?
Yeah, so for IDS-Fpga, we offer a lot of different outputs. So generally the main thing would be the RTL. So you get Verilog, System Verilog, and VHDL. But you, in addition to that, you have access to generation of the C headers, UVM RAW model, test sequences that we showed before, and again, a verification environment.
Okay. The second question is, you showed support for Vivado. Is there any support available for Altera?
So yeah, so we do have support for Vivado now. So we are working on introducing the Altera flow and integration with Altera. So that is currently in the works and will be available soon.
Okay, the third question is, you showed AXF4 Lite bus interface. Are there other buses available?
Yeah, so we showed the AXI4 light for Vado, but again, we do have support for other the AMP family like APB, HB. Along with that, we have support for other buses like TileLink and Avalon, of course, which is using that TerraFlow.
Okay, so that was it for the questions part. Thank you everyone for joining us for today's webinar. As a reminder, everyone will receive an email with instructions on how to review the PDF and recording for today's webinar. If you have any questions or would like to view downloads, we invite you to visit us at agnoses.com or send us an email at support@agnoses.com. We will see you next time. Thank you.